Well, thank you very much for this opportunity. I wish I could be there in person, but it's good to see so many friends and new people virtually, at least. So the story I'm going to tell today is, well, let's say the bulk of the talk today is going to be about the paper that appeared this morning on the archive with Enrico Herman and Jaroslav Trenka and Cameron Langer about loop integrand construction. But if I have time, time permitting, I'll talk a little bit about some of the recent advances we've had in loop integration technology and some of the more general structures of loop integrals that beyond what you heard from Claude last week. So, but before I get started with the details, I want to set the stage a little bit, in part because I know this is a school, and also in part because it didn't seem like Mark covered this last week, and I wanted to make sure that some of the big picture was clear to everybody about what we're doing in scattering amplitudes and about these, especially about these three programs, integrands, integration, and integrals separately. So I want to start with, what we understand about quantum field theory. So as we all learn in grade school, quantum field theories are usually defined by Feynman rules, by writing down a Lagrangian, and then the probability amplitude for any particular process can be computed by just summing over all the virtual histories, namely drawing all the Feynman diagrams. And an example, which is not quite an amplitude, it's really a ratio function, which I'm sure everybody knows quite well, would be the gyromagnetic ratio of the electron. So at tree level, there's just a single diagram that Dirac wrote down, well, not quite graphically, 1933, got his Nobel Prize. At one loop, there's another single diagram to do, which most students do compute as a homework assignment in a quantum field theory course. And this won Schwinger, Feynman, and Tominaga the Nobel Prize in 1947. At two loops, there's only 7 diagrams, but it still took 10 years for people to get the next correction to this particular calculation. At higher loop orders, the number of diagrams explodes, but maybe not quite as quickly as you might think. Doing the integrals turns out to be quite hard too. And what do we get when we're all done? As you all know, this particular prediction is the most precisely tested idea in all of science. But I want to draw your attention to a few aspects of this expansion that maybe your professor didn't dwell on when you took quantum field theory. For the first part, I think more people should be more embarrassed by the fact that that at tree level, or sorry, that at one loop, the result of this 1 week-long homework assignment is really just the number 1 times alpha over pi, which is the effective parameter in this expansion. And so we do a ton of work. And at one point in time, a historic amount of work just to calculate this number 1. You get this complicated integral, you have to do some expansions in the numerator, you have to learn about Dirac traces and stuff, and at the end of the day, you get 1. At two loops, which took 10 years to do, you'll notice that all of that work came into this little combination of zeta values, which I know Claude talked about, and Andrew McLeod, among others, probably. But you'll notice also that this expansion looks like it should be ordered. There are things that are weight 3, as Claude defined weight. Zeta 3, pi squared log 2 are both weight 3. Zeta 2 is weight 2, and then you have a rational number there. And it is natural to wonder if there is any way that we could somehow make the number theoretic properties of this particular number more manifest at the way we calculate it. Can we organize the loop expansion according to transcendental weight? Can we somehow short circuit the 10 years or even more the 30 years that it took to get to 3 loops and higher? Analytic expressions are now known for the 3 loops, and at 4 loops it's known up to, I think it's 5,000 or 6,000 digits, and almost everything else is done analytically. Yeah. But another aspect of the Feynman expansion that I don't think people spend enough time dwelling upon is that, while ultimately correct, it really does render them all but the most trivial predictions, those involving the fewest numbers of particles and the lowest orders of perturbation, either computationally intractable, until modern computers, things were really difficult, and even with modern computers, things quickly get out of hand, or just theoretically inscrutable. Even if you can calculate something for an experiment that's important, you might not have any theoretical control over it. And just to emphasize this, I want to mention this historic story that I think everybody who's interested in the S matrix really should know cold, but it's just useful to kind of step back and think about the history here. Scattering amplitudes are important for physics, not just because they describe the fundamental laws of nature and these fundamental probability predictions for a given theory, but because we do experiments where we need these background predictions, such as the LHC. For example, this process here where you collide two gluons and create 4 jets coming out. And for the experts in the audience, please ignore the muons here. Predictions like this, the probability for two particles to create 4 jets, were once literally viewed as beyond our reach. And to prove that, there was a paper in 1984 outlining the theoretical challenges to be faced by the superconducting supercollider, where they literally said the cross sections for elementary 2 to 4 processes have not been calculated, and their complexity is such that they might not be evaluated in the foreseeable future. Clearly, you need to know these background predictions to be able to discover new particles. And this theoretical challenge was a very serious one to people thinking about big modern day colliders in the 1980s. Well, there are very few ways of motivating people better than telling a student or telling young people that something is impossible. But before we get to the people who solved it, it's easy to see why nobody had ever calculated these processes. If you think about the 2 gluons goes to 4 gluons, at leading order, just at tree level, we're talking about 220 Feynman diagrams, thousands and thousands of terms, and millions if you try to talk about the probability, the squared S matrix. So it is very easy to see why this is just totally out of reach with pen and paper. Well, nevertheless, 2 physicists at Fermilab, Stephen Parke and Thomas Taylor, put their backs into it and really, really employed every conceivable theoretical and computational trick available to them. They introduced supersymmetry that they didn't need, an n equals 2 supersymmetry, which seems very silly today. They used the world's most powerful supercomputer at the time, or one of them, the heterotic supercomputer. Anyway, and as soon as they got the result, they rushed it to publication with this beautiful 1-sentence abstract. The cross-section for 2 gluon to 4 gluon scattering is given in a form suitable for fast numerical calculations. So they clearly had their audience in mind. Okay, now what did this look like? This is leading order, just tree level. We're talking about a rational function, not even a very good prediction for this process. Well, with a lot of cleverness, they were able to compress the result to a mere 8 pages. Okay. And this, you can't read this, but it doesn't really matter. It's just a big rational function. You have some matrices here of coefficients. But the reason why I really love this paper is because at the end of it, they chose to end this paper after apologizing for not giving any of the details of the calculation. They ended on this quixotic note. Furthermore, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist, but also a theorist's delight. Now, it turns out, I've spoken to both of them, and they had some intuition from the 2 to 2 and 2 to 3 processes that they knew that if they used some slightly more modern notation, that things simplified a lot. But they didn't really, I couldn't imagine what they expected when they wrote this sentence in this paper. But anyway, within 6 months, they must have stumbled on a guess. They stumbled on a guess which must have exceeded their wildest dreams. That's 8-page expression simplified into a single formula in notation that I'm sure you've seen already in the school, spinor helicity notation. But what makes this result so incredibly surprising is not just that it compresses 8 pages down to 1 line, which, by the way, they checked numerically. It wouldn't be another 10 or 20 years, depending on how you define it, before we really proved this and understood it. But what was really astounding is that it naturally inspired a guess for the n-gluon scattering amplitude, not just 2 to 4, but 2 to any number of particles whatsoever. And if this formula does not impress you, I don't think you have a soul. I mean, this is, when 2 gluons create 50, with 52 particle scattering amplitude, the number of tree-level Feynman diagrams exceeds the number of atoms in the universe. I mean, and so this remarkable compression should really be viewed as an indictment on the Feynman expansion, and the way we think we understand perturbative quantum field theory. Yeah, but of course, this is just, tree level. And, nowadays, especially with modern points of view, there are lots of ways of understanding this kind of simplicity at tree level. After all, it's not really all that quantum mechanical. And so, if you're a skeptic or if you're a pessimist, you might think, maybe things start getting bad. Well, if you think about the loop expansion, at one loop in 1994, Byrne, Dixon, Dunbar, and Kossauer showed that it was just the sum of a bunch of very simple integrals that you can evaluate pretty simply. At 2 loops and higher, it really started looking complicated again. And indeed, the strategy for finding a representation of this particular scattering amplitude at 2 loops and higher was really pioneered by most of these same authors, called Generalized Unitarity, that is going to form the majority of this talk. But this was put to use. So the basic idea there, and I'll come back to this in a moment, is to start with a complete basis of integrands, and then just fix all the coefficients by cut conditions. Well, this was done through truly heroic efforts by Christian Vergu in 2009. And what his representation looked like was this 12-page formula, which again, you can't read, but again, it doesn't matter. But again, it was valid to all multiplicity. So an incredible simplification. The number of Feynman diagrams grows with multiplicity. This is a fixed order thing. Well, as I hope you won't be too surprised by, within a few months of this paper's publication, my collaborators and I, from a completely different viewpoint, stumbled upon a similar guess that we were able to check. We had other ways of checking these things. And it turns out that whole 12-page expression reduces to a sum of single terms of that topology. And shortly after this paper came out, we got kind of ambitious, and we were able to push this to 3 loops. But I want to emphasize here that these formulas on this page were really in the spirit of the Parke-Taylor formula, in the sense that we had a way of checking a guess, and we made a guess, we checked it, it was correct. The actual proof or or understanding that this was the right answer, or why integrands organized so nicely like this, was really far from us in 2011. And one of the themes of my talk today is that this is no longer guesswork. It no longer requires cleverness to derive formulas like this. This is now a science, and it's a science not just in planar, maximally supersymmetric Yang mills, but in truly general quantum field theories. And that's really what I want to talk about today. Okay. But integrands are rational functions. They're dictated by ordinary Feynman propagators, by their cuts. They're very much more like trees than they are like loops. They're not transcendental, etc. And so if you're a pessimist, you might wonder, surely this can't survive integration. Well, to test that, unfortunately, requires quite a bit of work, because the first non-trivial multi-loop calculation, and by that I mean a function of multiple variables, so where it's not just a number, because who can say whether or not a number is simple or not, really has to go back to this 2 to 4 process. And probably the nicest one to compute is in planar maximally supersymmetric Yang mills, just for the sake of looking beyond this corner and seeing, is there anything nice to find about integrated expressions? And this is non-trivial, obviously, because most of those integrals in the previous page were infrared divergent, so you need to introduce regulators. To get a finite prediction out of this, a physical observable out of this, requires a ton of symmetry breaking work and gluing it all back together. Well, this was done truly heroically in 2010 by Del Duca, Claude Dewar from last week, and Smirnov. And they expressed their answer in terms of 18 pages of Goncharov polylogarithms, which by now you should all be very familiar with. And as you know from Andrew's talk, and as you should just know as members of the community, and following this talk today, you should not be surprised that within 6 months of this paper's publication, Christian Vergu, together with Mark Spradlin, Anastasia Volovich, and Goncharov himself, were able to find that that whole 18-page expression compressed down to a single line. And just as before, this kind of simplification was first discovered empirically by taking that long formula, putting it in Mathematica, computing something called the symbol, which you learned about already, and then trying to reconstruct this function. Why it's this simple is still, is a different question. But just as always, this has now been pushed, is no longer guesswork. It's now an industrial science. And this has been pushed now to this, instead of 2 loops, we now know this at 7 loop orders, which is an incredible application, but it took a long time to get there. One reason for reviewing this story, besides illustrating the points I'd like to talk about in this talk, is because I think it just illustrates the theme of scattering amplitudes, especially these days. And it's scattering amplitudes research is something like a virtuous cycle. It sometimes, but not always, starts with somebody just computing something, whether it's for practical applications or just because you're able to do it for the first time. So computing something beyond the reach of recent imagination. Compute it, any means necessary, and as soon as you get the result, you rush it to publication, and you put a 20-page appendix out there. And then shortly thereafter, somebody discovers something amazingly simple about these predictions, way beyond what anybody would have expected. Then you spend sometimes 5 to 10 years figuring out why. You understand its simplicity, you explain it, you explore its consequences, and then you put that understanding into new technology, and that allows you to compute something further. And if you stay in the scattering amplitudes business, you'll find yourself at various nodes on this cycle at various times in your life. And it's a very rewarding thing. And this whole time we keep learning more and more about the nature and structure of quantum field theory. Now, of course, this cycle is fueled by a lot of coffee, but because we're talking about quantum field theory in general, it really has applications to many, many corners of physics. Collider physics, obviously, but also gravitational waves, as you've heard about, early universe cosmology, and then a lot of pure mathematics, something like as discovered through the amplituhedron, for example. Okay, so with that kind of stage in place, I want to get started and talk a little bit about the construction of scattering amplitudes. And if I don't have time for anything else, this is I think the most important thing I'd like to do is just talking about the integrands for scattering amplitudes, but constructing them constructively. So, and as I hope you all know, we now have very powerful tools for both understanding and computing integrands in perturbation theory. We have recursion relations. There are things called Q-cuts. There's unitarity methods, which are the oldest. There are bootstrap methods. But the one that I think is the most general and the most powerful, has the most general applications, most powerful, is what I'm going to call prescriptive unitarity, which is just a slight refinement on unitarity. But the starring role, or the starring characters in all of these recent developments are these funny looking diagrams here, which are called on-shell diagrams, and they are the cuts of scattering amplitudes. So let me define those for you now, very briefly. So an on-shell function is really just an S matrix or networks thereof. So the simplest on-shell function is just a tree amplitude. But if you knew any trees whatsoever, you could start gluing them together into more complicated functions in a way that's dictated by basic principles of quantum mechanics. in any local or unitary quantum field theory, the meaning of a picture like this is perfectly well defined. Locality implies that the two processes, because the particle in the inside is on shell, it can travel an arbitrary distance in space and time. And so if you have a local quantum field theory, the left and right processes have to be independent, and so we have to multiply them. Unitarity dictates that the internal particle, because it's unseen, we have to sum over a complete set of states. And in particular, that means integrating over the on-shell phase space, and summing over all the other quantum numbers that can be exchanged between these. But I'm writing this here in a way to make it clear that it's defined in d-dimensional theories. It really has absolutely nothing to do with 4 dimensions or anything like that. And from this definition, it generalizes not just to a factorization channel like the picture there, but really to any network of tree-level S matrices. And it has been known for a long time that this data, this physical on-shell data, suffices to represent all scattering amplitudes and all quantum field theories to reconstruct. It encodes the full perturbative S matrix, the information of the full perturbative S matrix. And it'll be a large part of this talk to explain how that works, but I'm going to leave the discussion of the coefficients, these cuts, aside. They could teach a whole school on the beautiful structures there. But I want to step back a little bit and talk and be a little bit more theory agnostic for a little bit. So the basic idea of unitarity is that integrands are rational functions, and as such, you should be able to fix them by their poles. And rational functions you can express in terms of basis of rational functions. And so any scattering amplitude can be expanded like this. And where it becomes really interesting, I mean, this could almost be viewed as a tautology if you just took the actual amplitude as an integrand basis. But the reason why this is a powerful statement is that one can show, and I don't know if I'll quite show in this talk, but it's not very hard to see, that, for any quantum field theory, there is a finite dimensional basis, B, in which all scattering amplitudes at any given loop order, so all multiplicity, all external states, for any renormalizable quantum field theory, there's a finite dimensional basis in which all S matrix elements can be expressed to infinite multiplicity and regarding any external states. And that is very non-trivial. So it's just some illustrations of how this kind of works. I guess I didn't put the citation there, but Yaroslav Trinka and I wrote down a closed formula for the 2-loop S matrix in planar n equals 4, where we have these 3 integrand basis elements, and each one of them is multiplied by a coefficient with a very similar topology, not exactly the same topology. I'm going to come back to that later. And together with Enrico Herman, we extended this to 3 loops. And part of the point of this talk and the point of this recent paper was to generalize this to theories like the standard model in 4 dimensions and also to higher loop orders. So it's no longer just a statement about planar maximum supersymmetry. Yeah, but the basic idea is that once you've chosen an integrand basis, these funny pictures here, the Fs are completely determined by saying that the residues of the basis, of the vector in the basis, matches the residues of field theory, which we can compute on the previous slide, or are defined as defined in the previous slide. So to give you an idea of what this looks like, an integrand basis element like this, we could fix on a codimension 8 residue, which cuts those 8 propagators. And in 4 dimensions, you have a D4L, so that's fully localizes the loop integrand. And a cut that cutting those 8 propagators would have the topology of kissing boxes, not of the integral itself. But these are the only integrands in the basis that I showed you earlier. For 2 loops that have this topology inside of it. And so you can use this integrand to match that cut perfectly in field theory. So the bottom is the coefficient of the integral on the top. When you have fewer than 8 propagators in 4 dimensions at 2 loops, cutting everything still doesn't localize the loop integrand. And this is a subject of a lot of open questions and further research, but the short version is that at the level of matching an amplitude, it really doesn't matter. If your only goal is to write down an expression, because all you need to do is just cut these 7 propagator, cut every propagator you can, just so that the other topologies don't contribute to it, and then match it to the same coefficient at any points you'd like, or as many points as you need to soak up all of the degrees of freedom of that integrand basis element. But you'll notice also that these integrands are subtopologies of the double pentagons. So these double boxes are subtopologies of double pentagons, and moreover, if I added a double pentagon to these, or sorry, a double box to a double pentagon, it wouldn't affect the ability of the double pentagon to match the cut that I wanted, because I would, in order for me to add this to this, I would add a numerator to this integral that involved this inverse, 2 of the inverse propagators, one from this side, say, and one from this side, say, which would collapse to this thing. And because I'm multiplying by 2 inverse propagators, that numerator would vanish on the cut that we wanted to use in the basis. So this represents a slight ambiguity. I mean, not a slight ambiguity, a real ambiguity in how we set up the basis. Let me show you, there is I think a preferred way of doing this, and I'm going to try to get to that. And I want to illustrate this at one loop, although it seems a little bit trivial at one loop. Yes? Was there a question?
Yeah, sorry. Like I sort of like what is the difference between the white vertex and the black one? Sorry, you mentioned one is the coefficient, and the other one is the.
Yeah. So the shaded vertices represents S matrix. Represent cuts of amplitudes, tree amplitudes, and in these on-shell diagrams. I'm almost never going to draw them ever again in this talk. So they're mostly so the black vertices just represent vertices of a Feynman graph, a kind of a stand-in Feynman graph that doesn't necessarily come from a Feynman diagram in a quantum field theory. It's just a basis element. Okay. Let me try to illustrate this well, I'm going to draw those pictures again. So let me illustrate this at one loop. So at one loop, it's been known for a very long time that a complete basis of 4-dimensional integrands can be constructed by 4 gons and lower. So, and in dim-reg at least, you don't need to care about tadpoles or constants. And so you have a basis like this. Now, the number of degrees of freedom here are not important to us right now, but I'll mention them in a little bit. But the only integrands in the basis that have 4 propagators are these boxes, and so you use them to match the box cuts. And so the coefficient of a box integral in the basis is this leading singularity, or on-shell diagram, where there are 4 trees, which is in 4 dimensions is fully fixed. Now, what would the coefficients be in this basis for the triangles? Well, at first blush, you might say it's just the triangle on-shell diagram. Well, that's not quite right, and the reason is because every box in your basis also has triangle cuts. They have support on the triangle cuts. And so really the coefficient of this triangle is not the triangle, not the right answer. This picture here represents the right answer in field theory. And the coefficient of this integral in your basis is not the right answer in field theory. It's the right answer in field theory minus all the pollution that comes from your boxes in your basis. And similarly for the bubbles, it's the right answer in field theory minus all the coefficients of the triangles minus all the things that come from from the boxes. Now, this is a triangular system. And it's not very hard to talk about, to compute these things. It doesn't require a lot of linear algebra to just subtract a bunch of parent topologies that contribute to a given integral. But I want to emphasize, and this really won't be a theme of the talk, but it's really something I think for future work. I want to put my neck out and say that this is a bad idea. You do not want to choose your integrand basis arbitrarily and then fix the coefficients by linear algebra, no matter how trivial that linear algebra is. What is a much wiser thing to do, and we have a lot of evidence for this at 2 loops and higher when we have it, is to diagonalize the basis in cuts first. And so to call this whole thing your box integral, and to call this whole thing your triangle integral, and that. Now, the difference between this basis and the previous basis is basically trivial, and there's almost no linear algebra required in diagonalizing the matrix, and the reason is because it started off life as an upper triangular system of equations. So diagonalizing a triangular system is pretty trivial. But I'm going to argue that the combinations of boxes, triangles, and bubbles that appear in this like top line are better integrals to integrate. They have better properties. They're better suited for matching integrands, because if I call this now my new box, the coefficient is really just the box coefficient, the box on-shell diagram. And if I call this picture here my triangle, then its coefficient really is just the triangle. And this has a lot of very nice knock-on effects for integration that I'm not going to have time to demonstrate or really talk about, but just keep that in the back of your mind. But regardless of my intuitions about this, I think a very important question that should be in the back of your mind always is, what makes a basis a good basis? You can choose a basis arbitrarily, but it turns out to be a very subtle and interesting open question for active research to construct good bases. Okay, let me set that question aside for a moment and tell you about a stupid basis, which is nevertheless just exceedingly powerful. So this, what I'm going to describe now, generalizes OPP at one loop and to higher loops. But it's a really quite simple framework for understanding how to build a basis that is big enough for all scattering amplitudes in the standard model, say, in normalizable quantum field theories in general. So the basic idea is that the numerators that we talk about, so in this rational space or this vector space of rational integrands, we have denominator structure that's dictated by propagators. And we'd like to attach numerators. We'd like to talk about some numerators, because after all, if you have a quantum field theory with spin, you have numerators in your Feynman propagators. And the most natural language in which to talk about these vectors of loop-dependent polynomials, is in the same language as the propagator structure itself. And so let me introduce this notation here for just a generalized inverse propagator. And I can introduce this notation for the span over all vectors Q in d-dimensional space of inverse propagators. Now, this is a particular space of degree 2 polynomials in L. It's not all degree 2 polynomials in L, but it's a very specific space. And it's very easy to see that this space has a dimension of d plus 2, because the loop L squared is inside this space. Every one of the components is inside this space. I'll leave that as an exercise. And also the loop independent monomial is also inside this space. And so you have d components of L, you have d of these, you have one of those, and you get d plus 2. Okay, this is a nice little bit of representation theory. Well, it will become one. So obviously we need higher degree polynomials in general, and we can construct those by writing vectors in the sum of products of inverse propagators. And in the embedding space formalism, say, it's very easy to see that these are symmetric traceless representations of SOD plus 2. So we can compute the rank very directly. There's a nice combinatorial formula for it. Now, one thing that's kind of annoying, or it's not annoying, I don't know, one feature of this that I think you might recognize immediately is that because the loop independent monomial is inside L, I can always multiply by 1 and get a higher power. And so, in particular, the space of loop independent monomials, L to the 0, which is just the vector space 1. I mean, I should put square quotes in it because it's really has dimensions of mass squared. Doesn't matter. So you have this sequence of inclusions, and we're going to see several sequences of inclusions like that in this talk. And whenever you encounter a sequence of inclusions like this, it is very natural to define the complementary spaces. So to talk about the space of L1 that is not spanned by L0, which is only d plus 1 dimensional, and similarly for L2, etc. And so you can talk about, you can now stratify the space of, Q powers of inverse propagators into independent subspaces of different degrees. And while this actually turns out to not be especially useful for talking about numerators, the philosophy occurs many, many places. So I want you to keep that in mind. Now, I mentioned before that this space L does not include all degree 2 polynomials in L. In particular, it doesn't include any components of L squared. And this has some important implications. For example, in dim-reg, where we might write L as L squared minus some mu squared for some extra dimensional piece. So maybe you have a, where you have like L hat in RD, and then you have this thing in R minus 2 epsilon, for example. The combination is inside this space, not the monomial mu squared or L hat squared. So in particular, this has some knock-on effects for how you might construct integrand bases in dim-reg. This formalism and this packaging of loop-dependent monomials forces you to consider this pair as being primary and not allowing you to multiply by mu squared, for example. And so if you go back in the literature and you find dim-reg representations of scattering amplitudes at one loop in QCD, for example, this is not what people do. They usually write mu squared times the pieces, and mu squared costs us more because it turns out that although mu squared is not in L, mu squared is in L squared. It is in degree 2 polynomials. You can construct all of those things. So so the monomial mu squared is a very dangerous monomial. It costs you more in this formalism. That has some interesting implications for representing amplitudes in dim-reg that I think still remain to be fully fleshed out, but it's interesting. Okay, so we can talk about vector spaces of inverse propagators over propagators graphically as follows. So we can just draw this little dot on a line to talk about not just the Feynman propagator. Now everything is massless from now on, just for the sake of simplicity. But the vector space of numerators over that propagator. And you'll notice that this thing includes a spin 1 Feynman rule in any gauge. It includes the spin 1/2 Feynman rule. It includes the scalar Feynman rule and also a contact term, just the number 1, the constant piece. If I wanted to include, say, graviton propagators, I would have to include multiple copies of an inverse propagator over every propagator. Now, so diagrammatically, we can talk about integrands with their associated numerator spaces by drawing pictures like this. So this would represent a box with an inverse propagator's worth of degrees of freedom in the numerator. And we just saw from the previous slide that the numerator space on all of these boxes would be, on the first line, would be d plus 2 dimensional, okay? We could also, and it doesn't matter where we put it because the notation here is translationally invariant in L. And so any propagators that differ by any momentum are in the same vector space. And so we can talk about things with degree 1 power counting in the top line or degree 2 power counting in the second line. And one thing that this makes clear also is that because the vector space includes this constant here, we can see that this vector space includes contact terms directly. And so this d plus 2 dimensional vector space of numerators includes all of these contact terms, all 4 of them, which has interesting implications. For example, take d equals 1. So there's now 3 degrees of freedom on the left-hand side, but you see 4 scalar, now there's no numerators on the right-hand side. So you see 4 integrands, scalar integrands. And so this is how you can show, for example, that in d plus 1, these 4 triangle integrals cannot be independent. They have to span at most a rank 3 vector space. The left-hand side is rank 3. The right-hand side can't exceed rank 3. So you know that these things cannot be independent as rational integrands. Okay. Now, because this vector space of inverse propagators over a propagator includes all the Feynman rules for propagators in the standard model, it's pretty simple to see that if you draw a vacuum graph with these vector spaces on top of them, that it's going to include, by construction, every Feynman diagram in the standard model. Literally every Feynman diagram is an element of the spaces. And so we can talk about the zero-gon power counting. Zero-gon because as L goes to infinity, everything in this list scales like a constant, right? The inverse vector space cancels every element of the inverse vector space cancels the denominator. As L goes to infinity. And this list of graphs literally is going to include the loop-dependent part of any Feynman diagram in the standard model. So obviously the standard model lives inside this space. And the same is true at 2 loops and higher. So if we wanted to talk about 2-loop graphs, we just draw all vacuum graphs, and we're guaranteed that the standard model lives in this space. Now, I have not shown you yet that this is a finite dimensional vector space. That's what we're going to talk about next. So in any dimension, in any fixed number of dimensions, whether it's 4 or 4 minus 2 epsilon or whatever, an integer or with an epsilon of an integer, this space you can show is finite dimensional. And we can see this in the case here pretty simply. So what are these elements? What do I mean by B0 is this? This is the space of zero-gons. Well, say IQP is the space of Q inverse propagators over P propagators, okay? And so B0, what I really mean is the union of no inverse propagators with no propagators plus 1 inverse propagator over inverse propagator over propagator, et cetera, all the way up. And just as before, we have a sequence of inclusions. Because as it's easy to see, this vector space includes the element 1. And this vector space includes the element 1 and also single collapses. So these things have the same kinds of sequences of inclusions that we saw before. And as we saw before, it's a good idea to talk about the complementary spaces, which is the space of p-gons that are not expressible in terms of p minus 1 gons. And then thereby we can write these, this is the sum of the complementary spaces. And what we can show by more or less direct construction, which is what we're going to do, is that for any dimension D, the rank of these spaces eventually hits 0. And to do that, we just need to follow our nose more or less. So the rank of these spaces of numerators for a given p-gon in D dimensions is just the sum of these binomial coefficients. And if we wanted to talk about removing the complementary spaces, we would just, so here's the total ranks in various dimensions. So we have 2 dimensions, 3 dimensions. These are the total vector spaces we're talking about. But of course, we'd like to remove the contact terms. So we'd like to remove all the pieces that are proportional to 1 or more inverse propagators, and thereby define indirectly and recursively this top rank, the irreducible rank, and then define in terms of all of the contact terms. Now, this recursion relation actually is solvable in closed form, and it's the difference of 2 binomial, it's the sum of 2 binomial coefficients again. I didn't write that here, but you can find it in the paper that appeared this morning. But the point is that it's very easy to just solve this directly and write it down for any P and D, the vector space of top ranks, you know, how many irreducible numerators you have. And it becomes a nice little representation theory problem. And so, for example, you see that the constant is always a constant plus no contact terms. In 2 dimensions, we see that there's 3 independent tadpole numerators and 1 contact term, 4 independent in 3 dimensions, 5 independent in 4 dimensions. And we can really keep going, and we can just fill out this whole table. But importantly, you'll notice that it always hits 0 eventually, and that's pretty easy to see. You'll also notice that along the leading edge are always 2s. That's related to the fact that the maximal cut in any number of dimensions, or the leading singularities in any dimensions, always have 2 solutions to the cut equations, which get matched by the 2 degrees of freedom in the spaces. And some of you, if you're more familiar, if you know the literature very well, might recognize that those numbers in the bottom line, 179, I'm sorry, 9, 11, 7. Anyway, that is from being from OPP. So what we have, so just looking at one loop again, but now let's just restrict to 4 dimensions so we have some more intuition about it. We have all of these bases of integrands. So we're going to put a vector space of numerators on top of every one of them. And what we see is that for these zero-gon power counting, I haven't really talked about power counting yet, so I'm going to get to that in a moment. But anyway, if you put a vector space on every propagator, what you see is that you get 6. The 6 degrees of freedom for the tadpole break up into 5 one irreducible numerator and 1 contact term. The 20 for the bubble break up into 9 and 11 contact terms, etc. But you can talk about things with better power counting, with just lowering that number in the numerator. And so you can talk about tadpole power counting or bubble power counting, box or triangle power counting, or boxes or higher. And you can see that there's this nice kind of tower of integrand bases where there's also inclusions. Oh, I should have hit. Anyway, there are inclusions upwards. I'll get back to that in a moment. But we can continue to play this game at 2 loops and higher. And part of this is in our paper today. And so we introduced a graphical notation. It's very similar to what David and his collaborators introduced a while back. By labeling the loop dependence of any 2-loop graph by the numbers of propagators that differ by external momenta only. And there's the general vacuum graph has 3 structures. So you have 3 labels, and of course it's symmetric. So for example, 1, 1, 1, but we're allowing any of these indices to be 0, which would include product topologies, okay? Now, so from this, the space of inverse propagators, we just construct this. And if we knew those ranks in general, all we would do is just take a graph with propagators labeled by A, B, and C and put this vector space on top of it. And exactly analogously to one loop, we could just iteratively, recursively solve for the number of irreducible numerator degrees of freedom for every one of these things by this combinatorial rule. And in the paper, we wrote down closed formulas for this D, this math frac D, this top dimensional rank for what we call zero-gon power counting, in dimensions up to 4. So there's nice closed formulas for them, but we don't have a representation theoretic understanding of them. We've found them by brute force, and it would be very interesting to have that in general dimensions and also to have a rule for it. Now, this combinatorial rule about taking the total degrees of freedom, and decomposing it into top degrees of freedom plus contact terms is a statement about ranks, but it can just immediately be translated into a statement about vector spaces. So you can just read that same equation as being as literally a construction for the vector space. You take the total space and you can project off, you can take the null space of all of what's spanned by the contact terms, and that thereby indirectly and recursively defines your top level numerators. And we can keep going to 3 loops. So at 3 loops, we have 2 different topologies. We don't need to choose a routing. I'm going to get back to that in a moment, but just for the sake of concreteness, here's an assignment of L's to these edges. And to do the same thing, to represent amplitudes in the standard model, we would need this many degrees of freedom, or would be the total ranks, and then we could recursively compute the irreducible ranks for every integrand topology for any number of dimensions if we had an analogous formula to this, which we do not have. So, and they start becoming very large, so we haven't been able to compute them even empirically, or at least enough to fix all the coefficients we would need. So, but I suspect that some representation theorist, graph theorist, combinatorialist might recognize some of the numbers in these tables or recognize what's going on here and see how to get this out of representation theory of SOD plus 2. Okay. So far we just constructed a basis that's big enough for every single Feynman diagram in the standard model. That's not very pretty, and it's also not very, it's a little vacuous. What turns out to be much more subtle and much more interesting is to talk about how to stratify theories according to some proxy for, say, their ultraviolet behavior, maybe their transcendental behavior, transcendental weights, or something like that. And so let me give you an idea of what I mean. Before even talking about scattering, about bases, we can talk about just quantum field theories. And quantum field theories can be partially ordered by the size of the basis that you need to represent all of the amplitudes in the theory. So for example, really completely trivially, you can say that the standard model is bigger than the standard model without the Higgs, which is bigger than pure QCD and is bigger than pure Yang-Mills. And these inclusions, or these partial orderings, are all completely intuitive and trivial. The standard model has more Feynman diagrams than the standard model without the Higgs. So every ordering on this top line here just represents a strict subset of Feynman rules. So it's completely trivial that you need fewer Feynman diagrams to talk about Yang-Mills than you need for the standard model. What's extremely interesting is that this partial ordering exists even when it has nothing to do with the Feynman rules. So for example, there's a very strict sense in which n=2 supersymmetry is a bigger theory than n=4, which is a bigger theory than planar n=4. And that's very interesting. That Yang-Mills is a bigger theory than supersymmetric Yang-Mills might surprise you, because from the Feynman diagrammatic point of view, going to supersymmetry adds fields, adds lots of degrees of freedom, adds lots of Feynman rules. And so it's not at all obvious that the S matrices inside supersymmetric Yang-Mills would be smaller, or would require a smaller basis. And of course, they do, and one way to understand that is to do with the ultraviolet behavior of these theories being better the more supersymmetry you have. And so this kind of set of inclusions reflects the UV behavior, the power counting in quotes, and it's important that they're in quotes because part of the point here is to clarify what someone might mean by power counting. And it's exactly in this sense that the standard model, the basis required for the standard model that we just saw how to construct, is a bigger basis than what we need for n=2 super Yang-Mills, is a bigger basis than what we need for n=4, etc. And it's this partitioning of a basis into these kind of slices, these subspaces that behave better, that represent theories that behave better than other theories, that turns out to be a very interesting and very subtle, and I would say mostly unanswered question. But I'm going to put forward one proposal here. So one way to summarize what I think is a hugely important open question is, can we define a basis that is big enough for scattering amplitudes in n=4? So can we define carving out the subspace of the space that we just talked about of just integrands that are good enough for n=4? And in the planar limit, we know how to answer this. But as soon as you go to non-planar amplitudes, this is a fundamentally unanswered question, or at least, beyond 7 loops or something. So, okay. So first, let me explain how this works in the planar case, because their power counting really is the right metric, or at least a very good metric. And that's really what everybody means when they talk about power counting. So the first thing is that for a planar Feynman graph, there's or really a plane graph, because it has to be embedded, there's a natural way to assign loop momenta variables to the graph, which is associated with a dual graph. And for various reasons, you need to symmetrize over all these dual variables, and there's a very simple definition. An integrand has p-gon power counting if, as L goes off to infinity, as any L goes off to infinity, it scales it like a p-gon or better at infinity. So it has p propagators, net propagators as L goes off to infinity. And this is a perfectly valid and very useful definition, and is easy to see dual conformal symmetry or other aspects of special cases of p-gon power counting. But anyway, once you have a definition of what power counting is, we can talk about the space of all integrands with p-gon power counting. And again, it's not hard to see that these have a sequence of inclusions. We can talk about the complements, and therefore we can represent an amplitude in a basis of integrands with specific p-gon power counting, or better. And then moreover, we can actually construct an amplitude iteratively according to the power counting behavior. So for example, I can talk without any ambiguity about the foregone power counting part, or the box power counting part of the standard model in the planar limit. As we'll see, in the non-planar case, it becomes much more subtle. But in the planar limit, where all of this is very well defined, it's completely unambiguous to talk about the box power counting part of the standard model, or the triangle power counting part of the standard model. And you can fix these things in pieces. And the basis that you need for n equals 4, as most people should know, are boxes. But that's actually a little too weak. So for planar n equals 4, we actually know that amplitude integrands are dual conformally invariant. And the space of dual conformal invariant integrands is a subspace of all of those with box power counting. And it turns out that n equals 4 is a subspace of dual conformal invariants too. So we don't really understand how to do this last partitioning here, but we certainly know how to enumerate all dual conformal integrals. And we know that n equals 4 lives inside that space on general grounds. But even dual conformal invariance is not really optimal in a few ways that I'm going to come back to at the end here. So for example, a dual conformal invariance is not strong enough to guarantee that an integral is UV finite. Starting at 8 loops in the standard in planar n equals 4, you get these divergent integrals term-wise. And you know that the theory is UV finite. And so it becomes a problem with the basis. You're representing an amplitude which is finite in a basis of things that are not finite, which is a bad idea. So DCI is not strong enough to exclude that. It doesn't guarantee maximal transcendentality. At 3 loops, there's a very simple 3-point graph, 3 massive point graph. And if you wanted this n equals 4, you could make it a 6-point graph. And this thing evaluates to 20 times zeta 3. It's not zeta 4. So it doesn't ensure full transcendental weight. Wouldn't it be nice to be able to talk? It is widely expected, and there's a ton of evidence for it, that n equals 4 is maximally transcendental. And so an integrand like this should not appear in your basis. And how do you exclude it? How do you test that it's not maximally transcendental? I don't know, but I can do this integral. It's 20 times zeta 3. And it forces a certain kind of over completeness in the basis. And this only appears beyond 5 particles. So maybe you don't care about it too much. But ultimately, it requires that we include integrands with more propagators than there are to cut. And that space of integrands turns out to be overcomplete. They satisfy algebraic relations amongst themselves. And therefore, you need to throw out subsets of a given topology to make your basis, to eliminate the redundancy in your basis. And that is almost always a really bad idea. So it does not give us a triangular system for the cut equations. There is actual linear algebra to do for the cut equations, and worse yet, that linear algebra is not topologically agnostic. I mean, it's going to have to care about how you label the legs on the graph, which is a very unfortunate feature of box power counting in the planar limit. We saw this, so Enrico Herman, Jaroslav Trinka, and I showed that this problem rears its head at 3 loops. It can be avoided by reasons that we didn't understand. We just got lucky at 2 loops. But at 3 loops, it represents like one little bit of magic that has to happen in order for your over completeness to not screw things up. And at 4 loops and higher, I think all the people who thought about it are pessimistic about figuring out about this over completeness problem. So it's a little bit more subtle, but I just wanted to mention it. Okay, so let's talk about power counting stratifications. And the planar power counting matches what I'm going to define as power counting at 1 loop for the simple reason that every graph is planar at 1 loop. You always have a p-gon where the propagators can be ordered such that the difference between adjacent propagators is an external momentum. Or the momentum flowing through two propagators differ by an external momentum. So instead of talking about, so remember, call this definition here of Q inverse propagators over P propagators. Well, we can say that this is an element of the basis with P minus Q gon power counting. And so just as we defined the zero gon power counting basis, which is big enough for the standard model, we could similarly just, in the same breath, talk about tadpole power counting bases, bubble power counting bases, triangle power counting bases, etc. And it's, again, I want to emphasize here that there are inclusions, that these things include this way. And moreover, they include, column by column here, so that this is an element of that, this is an element of that, etc. So you have all the same kind of normal partitioning the partitioning that we saw before. Would be a good idea here too. But for any of these power countings bases, we can define the top rank recursively in this way. And I'm not giving the formula here, but it's in the paper. There is a closed formula for the top rank of a Q-gon with P-gon power counting in D dimensions. So for any Q, P, and D, we have a closed formula for both the total rank, which is trivial because this total rank is just that original binomial sum of binomial coefficients, and we have a nice closed formula for what that thing is in any P, Q, and D. But anyway, again, structurally, it's the same story. We're taking this total space and we're just decomposing it into the subspaces spanned by contact terms. And so thereby you can see that the ranks attached to these base integrand bases get organized as follows. And moreover, when you stratify in this way, you can see that I lost it. I don't want to go back. That you can talk about the 4-gons power counting basis that's not representable by 3-gon bases with worse power counting, and so on. And thereby organize your loop-dependent numerators in a very clever way, or in a way that's, well, that tracks very closely to what people have always done at one loop. But importantly, this doesn't generalize nicely to non-planar ways, and for reasons that we'll encounter. So for any planar graph, we can just define the power counting in this naive sense, but this really requires that we have an assignment of the loop momenta to the graph. And that comes from the plane embedding of a planar graph. But as soon as we lose that plane embedding, or as soon as we talk about an intrinsically non-planar quantum field theory, we lose all of that. And so just to illustrate this, and it's kind of a little pedantic, but if you look at this particular example where we have a box and a triangle, everybody would look at this and say that this loop scales like a box and this loop scales like a triangle, obviously. However, I can draw it in multiple ways. And why don't I say that this scales like a pentagon integral, and this thing scales like a box, or a pentagon and a triangle? There's no intrinsic way to, until you choose an assignment for the loop momentum. This definition here is imprecise and ill-defined, and so when we are encountering a non-planar graph or a non-planar quantum field theory, we somehow have to deal with the fact that this kind of polynomial degree power counting requires a reference to how you labeled the graph, and this is a very bad idea. It means that it certainly can define a well-defined partitioning of your basis, but probably not one that has any meaningful strata in it, or any very useful strata where nice quantum field theories live in nice power counting parts. Another example of this would be this kind of wheel integral here. And it's natural to see that to call this integral to be the sum, or to have box power counting, because all three of the loops have 4 propagators in which they're involved. So as any one of the L's goes off to infinity, you get 4 propagators that turn on. But an equally symmetrical way of labeling this graph would be to label it this way and say that it's 4 boxes. And I claim that there is no good way of associating or a unique way of or minimal way of labeling the graph. So for the graph theorists in the audience, or if you know a little bit more graph theory, this routing of loop momenta corresponds to a choice of cycle basis. And in the space, and if you go to high enough loop order, if you look at graphs with very high Betti numbers, the number of possible loop cycle bases grows extremely large. And something as a metric as simple as choose a basis where the smallest cycles are involved is not specific enough. There's usually many, many solutions to those, to that criteria. So in the space of cycle bases, I do not know of any intrinsic minimum or preferred cycle basis to define power counting in this naive way. If somebody knows one, I'm very interested, but I'm kind of skeptical that it exists. So in this recent paper, we proposed a graph theoretic definition of power counting that I'm going to explain right now, which has nothing to do with a way of routing a loop momenta. It's entirely defined graph theoretically by just saying that this integrand is designed to scale exactly like another integrand or another set of integrands at infinity. So let me show you how it works. It's pretty easy to see by example, and then I'll get to the definition. So say that we have this integrand in our basis, and we'd like to construct integrands that scale exactly like this one at infinity. This is pretty easy to do. You just add a propagator to this graph, and you add the whole vector space of inverse propagators on top of it. So for example, if we had this integrand, which includes that one as a contact term, we could just include that vector space of numerators. And by construction, this integrand with this numerator space will scale exactly like that graph. And similarly, we can keep going, and we can construct a full infinite tower of graphs that include a given graph. And by construction, this whole infinite tower scales like that given graph at infinity. This is now entirely graph theoretic. Again, it doesn't matter where that little dot is drawn, as long as you can move it by translation to anything, you can cross external edges. But it turns out to be equally easy and probably pretty useful, if not important, to not talk about the scaling, a basis that scales like a given graph. So to define, instead of like 3-gon power counting, you could say this graph power counting. It turns out to be much more useful for quantum field theories to talk about power counting that scales like one of a given graph, a number of graphs at infinity. So for example, instead of taking this integral as your scalar or your representative for power counting, we might draw this one, and then we could start drawing all the graphs that include that graph that scale exactly like that graph. And you'll notice that some of these graphs have multiple ones. This one here collapses this way. It also can collapse that way. So there's multiple numerator spaces we can put on it, and like it'll scale like this or like that. And the simple rule is you just add all the vector spaces. And so the power counting basis that scales like this set, this one or this one, can be defined as by adding up all of the vector spaces that will lead you to one topology or another, and then just taking the full span of those vector spaces. They overlap a lot, so it's sometimes a little hard to compute the rank, but it's well defined. And thereby you can construct a basis with, and by that same recursion, according to constructing vector spaces in terms of their contact terms, we can recursively define the irreducible or the top level rank for any particular integrand. And so all that we need to do to put this definition to use is to define a set of graphs that we're going to declare to be scalars, to have numerator 1, or we can give them any numerator we'd like, but the point is that we're going to construct a basis that all scales like a given set of integrands. And for the sake of concreteness, let's just put the numerator 1 on top of all of them. And so we're going to define a scalar p-gon as a graph that has girth. This is defined at any loop order, by the way. It's a graph of girth p such that all edge contractions have smaller girth. So girth, remember, is the size of the minimum cycle. The smallest cycle so the smallest loop you can find in the graph is the girth of the graph. And if you collapse any edge of the graph, you get something with smaller girth. I call that a scalar, okay? And so we can now look at this and we can see that here are the scalar 1 gons. Here are the scalar 2 gons, the scalar 3 gons, scalar 4 gons, scalar 5 gons. We can construct this, and we can also go to arbitrary loop orders and construct these scalar graphs and recursively define this very large integrand basis that all scales like a scalar p-gon, one of the scalar p-gons at infinity. So let me show you what this looks like in a slightly more complicated example. Let's take this integrand here, which would have been labeled 3, 2, 3 in the previous notation. If we wanted it to scale like a 0 gon, like a constant, we would just add the vector space of every inverse propagator to every propagator. And so we would get that kind of numerator space, which is a pretty big vector space, but still. If we wanted to talk about 1 gon power counting, we would add together these different vector spaces, which represent all of the ways of collapsing this graph down to the right-hand side, to one of the scalar graph. If we want to talk about 2 gon power counting, we would add up all of these vector spaces and talk about that numerator space. And we can continue going for 3 gon power counting, etc. And so I just want to be clear that these vector spaces are dimensionally agnostic. They have nothing to do with the space-time dimension. They're well defined for any p and any graph. If it does not include it, so for example, this graph does not include any of these graphs as a any of the 5 gon graphs as a subtopology, then we don't, sorry, that's not true. It does include it. Yeah, sorry, it does include it. And it would be scalar because it's one of the scalar 5s. Yeah, anyway. So again, we can define this rank, and again, we can view this rank formula as being a way of constructing the numerators directly. And we can continue to higher loops. So in this paper that came out this morning, we included an application that we thought was pretty, maybe not phenomenologically motivated, but Amplitudes community motivated, which would be constructing a basis of 3 loop integrands that should be big enough to represent n equals 4 amplitudes beyond the planar limit, all multiplicity, all end of the KMHV, all amplitudes. And to do that, we chose triangle power counting for the reasons that I alluded to before about conformal invariance. But anyway, so we constructed the 3 gon power counting basis at 3 loops for 4 dimensions. And so the 3 gon power counting scalars at 3 loops is now a longer list of things. And in terms of this notation, how we labeled the graphs, this is what they would look like. And so we can construct, for example, what is a numerator of this graph, this particular ladder graph? Well, again, it's just the sum of all the vector spaces. The notation changed slightly from slide. What I draw as a circle with an empty circle here was filled in with the white on the previous slides, but it means the same thing. In the paper, we use these conventions. The talk is mostly using a different convention. Anyway, so you just add up all of these vector spaces. And in any number of dimensions, you can compute the total rank. And in any number of dimensions, you can do this decomposition into contact terms, etc. And so in 4 dimensions, for example, we compute the rank of this space, and we find that it's 984 dimensional. I mean, that's huge. But it decomposes into 952 contact terms, leaving only 32 at the top, which is interesting. So anyway, and included in the work, we had an ancillary file that just listed all of the graphs and these ranks and how their breakdowns and all the story. So the vector spaces of numerators, etc. We included all that as a Mathematica notebook. Okay, but I want to make clear that this definition of power counting, while as far as I know, is the only graph theoretic definition that exists for non-planar integrands. I don't know of any other one. I mean, besides trivial modifications. We know that it's not good enough for answering that question of, say, constructing integrands big enough for n equals 4 in a good slice. Obviously, integrands in n equals 4 live in the same basis that you represent standard models, amplitudes. So that's a triviality. What I'd really like to define is something like box power counting, such that n equals 4 lives inside box power counting, and I want to define box power counting in some way that is non-planar and graph theoretic. And unfortunately, we know already that this definition of p-gon power counting is not good enough for n equals 4 for a pretty trivial reason, which is that our notion of p-gon power counting is not compatible with planar power counting at high enough loop order. And the easiest way to see this is just with some examples. So, for example, this planar graph here on the left, this triangle with this triangle of bubbles, meets our definition of a scalar two-gon, a scalar bubble integral. But in a planar theory, we could assign a numerator and still call it a scalar bubble. Call it a bubble integral by the ordinary dual variable map. And similarly, this box with three triangles would be called a scalar triangle in our definitions. But this is where it becomes relevant for n equals 4. This pentagon surrounded by boxes would also be called a scalar graph in box power counting at 6 loops. Okay, and that's a problem because the planar graph of this topology, which is an instance of this topology for sure, if given numerator 1 is not dual conformal. And if you put the dual conformal numerator on it, it wouldn't be in our basis. We would declare that to have worse power counting. So to set another way, just to make it clear, n equals 4, it's known that n equals 4 amplitudes, the planar n equals 4, sorry, I should have really added here, planar n equals 4 is a subspace of all dual conformal invariant integrands, which is a subspace of planar power counting planar foregone power counting. And unfortunately, this is not a subspace of non-planar foregone power counting. So our definition does not, said another way, the foregone power counting basis that we construct, we know would not represent n equals 4 amplitudes beyond 5 loops, and we know that triangle power counting in our definition wouldn't represent n equals 4 amplitudes beyond 7 loops. So this is clearly an unsatisfactory answer. Although it does carve up the basis, the nice theory doesn't live at the top. So I've got 10 minutes left and I want to leave a little bit of time for questions. So instead of talking about integration and stuff, I just want to talk about ways that we can improve, open questions and strategies for constructing a better basis. And so suppose you followed what I just, the last 20 minutes or so, and you constructed an integrand basis for n equals 4 amplitudes at 3 loops, and you wanted to somehow now represent an amplitude. Well, if you constructed them literally the way that we just did, you would get, you start off with this very large vector space, then you project off of it, giving you these pretty much random numerators. And it's always a good idea to organize your basis of numerators according to physics. It's always a good idea. And in particular, it's a good idea to make this triangular basis, it's a triangular basis with triangle power counting or worse, make it sparse. Make it as sparse as you possibly can make it. Or if not sparse, make every single element of this basis as physically meaningful as possible. So for example, together with Simone and Yara, Simone Caron-Huang and Yaroslav Trinka, we have had a triangle power counting basis of n equals 4 amplitudes at 1 loop. That had an interesting property, which is that the triangle integrals there were chosen so that they matched infrared singularities exactly. So it wasn't a sparse basis, but it was one that made the infrared structure of the theory clear. You could have chosen a more sparse basis, but that's one that's well motivated by physics. The problem is that at large enough loop order and large enough multiplicity, which is the case that we're considering here, the general case with lots of legs, there aren't usually well-motivated places for where you should have these amplitudes vanish. in general, and I'll show you what this means. But before I show you the obstructions, we can just see an example where it works very nicely. So this happens very well when the integrands are polylogarithmic. And the reason is because if it's a polylogarithmic integral, it has maximal codimension residues. It's d log all the way down. I don't think that's been proven. Oh, sorry, so it's certainly not even true. You can write polylogarithmic integrals as sums of elliptic integrals. But often the case when I have a Feynman integral integrand in my basis that I know is d log. And when it's d log, I can match the maximal codimension residues of that integrand are all very specific places in loop momentum space. And those very specific places, I know what amplitudes do on all of those places. Namely, they're leading singularities of some topology. And so, so there's physical meaning there. And so when you have lots of polylogs, when the amplitude is mostly polylogarithmic or almost entirely polylogarithmic, you really have a lot of physical intuition for how to organize that basis. And one application, so unfortunately this doesn't work very well in general for general amplitudes, but it works better with low end of the KMHV degree at low loop orders and at low multiplicity. And so to illustrate this, a case which is as close to polylogarithmic as you can at 2 loops beyond the planar limit would be MHV amplitudes, in which case you have these leading singularities to match. And it turns out, without too much difficulty, we were able to construct a basis of integrands that exactly match every one of these leading singularities. And we were totally guided by the fact that we knew that every one of these, that most of these integrands were mostly polylogarithmic, and we had to match everything there. The problem is that there are places where we can't take that last cut or last couple cuts. In particular, these 2 integrals here are known to not be polylogarithmic in general. And so even though on general grounds, by arguments that are not hard to show, it's not very hard to show that these MHV amplitudes absolutely have to be polylogs at 2 loops. Integrand by integrand in your basis, you have these integrands that include K3 integrals in general. Integrals over Calabi-Yau twofolds. So they're very far from polylogarithmic term-wise. And this obstruction is still an art form to cancel this. And it's something that you can check in post, but it's very hard to organize. And the organizing principles for how to deal with, how to choose representative numerators for an integrand that is polylogarithmic or maybe has polylogarithmic parts is a big open question. Another way of saying all of this is about integrand purity. And I don't know if Claude talked about this or not, but when the basis is d-log and all evaluations are just residues, then diagonalizing on cuts guarantees that the integral is in canonical form, uniform transcendental and upper triangular. So the differential equations are beautiful and the integral is easy to integrate. But when there's no d-log form, what do you mean by purity? And some examples of integrals that are in this new class of things that are worse than polylogarithmic that Claude did talk about are these Calabi-Yau integrals, which are relevant for planar theories, non-planar theories. They turn on a little bit sooner for non-planar theories, but still. Where we have a Calabi-Yau one-fold, an elliptic integral, a Calabi-Yau two-fold, which is K3, Calabi-Yau three-fold, etc. And they're very special Calabi-Yaus, by the way. These are quotients of the idiot's Calabi-Yau, or the first one you learn in every book, which is a p+1 degree polynomial in degree k plus 1 polynomial in pk, hypersurface in degree k. And there are examples involving massive quantum field theories these massive bubbles have the exact same Calabi-Yau structure. It's been known for quite a while. But even in massless theories, this turns on eventually. Okay, that's all I wanted to say about that. Anyway, there is great room to improvement. So one of the points of this talk was that we can organize a basis of integrands such that we can match a quantum field theory piece by piece, and that all of the work we did, the whole basis that we needed to construct for n = 4, is there for the standard model. And moreover, it represents the maximal transcendental part of the standard model. That's not saying the theories are the same. Their coefficients are very different, but all of the integrals you need to do, all of the hard work is identical. And you can match an amplitude by power counting iteratively, and power counting tracks transcendental weight in some vague way that I'm not going to get into. But it would be much better to organize these bases in a more meaningful way. So for example, for one thing, when you don't have enough propagators to find, when you don't have leading singularities, what are the right choices what are the representative numerators in your space? And I think the answer to that is that we trade evaluating at a point, which just means fixing a polynomial at, you know, a degree k vector space at k points, by period integrals that are very, you know, particularly chosen. I could talk more about that if anybody's interested. Or another thing would be to stratify them by actual ultraviolet behavior. You know, not this proxy for ultraviolet behavior, but the actual UV behavior. Like, what is the leading pole in the epsilon expansion? Or transcendental weight, whatever that means. Nobody's been able to provide a robust definition, and certain mathematicians are kind of skeptical that a definition exists, but colloquially, physicists talk about transcendental weight just, you know, all the time. And even colloquially, it would be really nice to organize an integrand basis according to transcendental weight, which is some proxy for saying box power counting, say. You would like to say the leading weight part, the maximally transcendental part of a basis, should have n equals 4 in it. How do I define that subspace of integrands? Or maybe how the integrands get partitioned into dimreg. Dimreg really does organize the numerators in a peculiar way that makes it very easy to correct d-dimension, you know, to upgrade d-dimensional integrands into d-2 epsilon dimensional integrands. And the precise way that works is still kind of a subject of ongoing research, but it's clear that the way you construct integrands bases for dimreg should be informed by this kind of story, and should inform the story, vice versa. So I see that my time is up. Conveniently, I've gotten through part 1, of, which is okay, because the other ones were extra slides. This is a good place to end the talk. So I realize I'm out of time, but if there's any questions, I'd be happy to take some.
All right, thank you, Jake. Any questions?
Yeah, hi, I had a question. So initially you looked at the UV behavior, right, for the integrand, constraining the integrands by looking at the rest UV behavior.
Mm-hmm.
But in the end, you mentioned something about the fact that you could also have the sparse basis by looking at IR finiteness of the. So is there a way to like simultaneously implement these two constraints? I mean, naively they would seem like you know, they are in sort of tension with each other.
Well, you know, I hope so. I hope so. Let me. I mean, I guess I would say ideally, you'd love to be able to do both. And maybe the way that people have done things at one loop is already a suggestion for what we'd like to do, which is where you have a mass regulator for the infrared and you have dimreg for the IR, the UV, mostly just so that you can partition off the IR structure from the UV structure. Whereas in dimreg, they mix them both up. But the problem is, and this is where it starts becoming really interesting to think about for future research, is that when you start constructing integrands in a regularization scheme, the structure of those integrand in your basis becomes regulator dependent. It doesn't mean it doesn't mean that your finite correlation functions or cross sections will be, but it means that you're representing it in now a regulator dependent way. And that regulator, there's some evidence that dimreg is kind of bad for transcendental weight. And the easiest example of this, it would be to take the bubble integral in 4D. It integrates, it's a 1 over epsilon plus a log plus 2, plus the number 2. And there's no way to add a loop dependent, at least I don't know of any way to add a numerator to that integrand to get rid of that 2. And so it's clear that in just dim-reg straight up, your integrand basis won't be uniform in transcendental weight. In mass regularization, it is, but then what the hell do you do with the UV? You know, you have to regulate the UV. So there's a lot of things to move around and to compare. I mean, I would probably do something combining the two, like Byrne and Morgan did in the 90s, where you have mass regularization and dim-reg. But you know, it remains to be seen how much you can organize the basis to reflect the right structure, to reflect all this, the UV and the IR separately.
Okay, thanks. And the maximum transcendentality, so your new basis, I mean, is that I mean, you posed a puzzle, right? Initially, that there was a problem that some of the things were not satisfying the maximum transcendentality. So the new basis.
Oh yeah. So so there's a true statement which is like the flip of what you would like. So when I construct the triangle power counting basis, I know that basis includes in it all of the maximal weight stuff. However, it doesn't mean that the basis is pure or is uniform. So there's lots of lower weight crap that's in there too, that has to cancel out. And I don't know of a good way, you know, for example, I mean, that planar wheel integral that's zeta 3, I don't know of any good definition of power counting or otherwise to kill that element from your basis. If you draw an integral that's bigger than it, it has more propagators, it has it as a subtopology. And sure enough, if you do one of those integrals, you get something of weight, in this case, weight 4, or sorry, weight 6. Did I say zeta 3? I meant zeta 5. Anyway, you get something of weight 6 plus this 20 times zeta 5. And it's just like a bare pollution in almost every integral in the basis. And so there's a filtration of transcendental weight, and the best power counting bases have all of the maximal weight pieces. But they also have all those slower weight stuff that, you know, you don't get right until you go to a worse part of the basis.
Yes, thanks.
You mentioned at the end about maybe using mass regulators for the IR and dim-reg for the UV. There's a kind of an obvious thing, which I'm wondering if people have looked at, they've probably looked at. There's a big class of theories, including pure Yang-Mills, that you can get from just n equals 4 by giving masses by hand. So you can calculate the UV by giving masses to, you know, any of the superpartners you like to n equals 4. And of course, you can regulate the IR if you like by going out along the Coulomb branch a little bit. But now I'm not saying that. I mean, it would be extremely interesting to compute amplitudes for those for that n equals 4 theory with the masses. I think they're called n equals 2 star, n equals 1 star theories, or even n equals 0. But given that you know there's some underlying D-log form, presumably even a nice form with like with unit leading together and so on, just deformed by the masses, does that help inform what this kind of basis should look like? I mean, this should also be true beyond the planar limit.
Yeah, absolutely. I mean, at one loop, I think absolutely, and it's a practically, you know, that's a strategy that I'm pursuing with my student Kokomides, who's in the room, I think. And this is, I mean, these are great questions. So, and it turns out if you just go back to this old literature where they did, you know, pure Yang-Mills at one loop, it's full of possible improvements. You know, just you rotate, you make it D-log wherever you can, and you immediately see a ton of coefficients drop out, or you make it, you know, unit. The basis really does get organized better from this modern perspective, and from thinking about D-log, from thinking about purity and transcendental weight. But that's, I mean, so at one loop, the answer is absolutely yes, and we're already along the way to trying to learn those lessons. At 2 loops and higher, absolutely yes too, but it just seems like a little there's a little bit less data sitting around. I mean, how many pure Yang-Mills 2-loop amplitudes are known at the integrand level? But great question, Nima. Yeah.
So Jake, what do you mean in your last slide? What do you mean by trait evaluations for periods? I don't understand.
Yeah. So I wish I had my figure up. Maybe I can find it. Let's see. Yeah. No, it's not that figure.
Nick, I mean, do you mean just to the extent that we can think of the leading singularity itself as a big contour rule that we just back off from the highest dimensional tori and talk about periods of arbitrary dimensionality?
Absolutely. That's basically it. Exactly. Although I don't even want to do periods of. I want to do periods of maximum dimensionality. So.
Okay. Sure. Of course.
Yeah.
Right. So when we aren't available, you just back up to whatever period, whatever the lowest dimensional integral is that you can well define on cut.
Yeah. So I mean, an example that would illustrate this is here, where so I could find a simpler example of this, but this integral on the left-hand side has d-log parts. It absolutely has leading singularities, and I would expect it to be a polylog. However, because it has these elliptic pieces inside of it, these integrals on the right-hand side are generally elliptic. So if you do this integral, and it's not that hard to do a lot of these integrals, you find that it's polylog stuff plus elliptic polylog stuff. And there's a question is like, can you combine them in a way that such that the combination is pure polylog? Can I define the d-log part of this integral or not when there's elliptic topologies sitting around? And the answer to that, I think, is almost certainly yes. And you diagonalize, in addition to the contours, the toric contours of the leading singularities, you also diagonalize on the subcycles of the torus. So like you choose to make a basis element that vanishes on the A cycle or vanishes on the B cycle or something. That definition generalizes to the Calabi-Yaos very cleanly. It becomes very impractical. I mean, I don't think anybody knows how to do those integrals once. It also results in a basis where the coefficients of the integrand elements are now ratios of periods of Calabi-Yaos, which I would like to call that algebraic or something, but it's I don't know. I'm still personally a little scared of dividing by a number that I would like to assign to have transcendental weight.
Also, maybe I misunderstood. When you say you have the 2-loop non-planar MHV integrands, right?
Yeah.
And you have some part that will integrate to like elliptic multi-polylog or something. But how do you know the final answer must be multi-polylog? Is that obvious?
Oh no, I mean, let's see. I mean, it's obvious is is always a loaded question. The easiest way to see it, to at least show it, which shows that it's not very obvious, is that so this is very post facto. In the representation that we wrote down, there's a little at the end of like the third section. We show that the cut on the K3 surface, the integrand is identically 0. And so it just completely vanishes on the K3 surface. But it comes from the combination of all of these integrals that have that support on that subtopology. So it's a non-trivial cancellation. Yeah, what's the easiest proof that it should have been? Maybe there isn't an elementary one, but there's certainly conjectures that amplitudes, and I mean, including some that Nima and I have worked on, we've put forward a conjecture saying that it should be d-log. But
I mean, in the planar limit, of course, but also for non-planar, you mean you?
Well, we made the conjecture for non-planar. There isn't.
Yeah. Okay.
So,
yeah. You mean from the leading singularity and so on? Yeah. Okay. More questions, comments?
So there was this paper by Byrne on this evidence of non-planar amplituhedron. I mean, is this does it somehow tie up with that? I mean, the fact that there was some evidence for d-log for the non-planar case.
Sure. So at low well, regardless of the multiplicity, the amplituhedron really tells you a lot about the structure of the cuts, and there are, I think, in every amplitude at any loop order, there's going to be certain directions that are screaming to be called logs, you know, where they're purely logarithmic all the way down. I think that's a separate, so that those, I mean, like, so the evidence for some polylogarithmic structure there is maybe a little independent of the non-existence of other things, but of the non-polylogarithmic stuff. But there's also a sharper statement to be made, which is that for low multiplicity, you know, you can avoid these elliptic structures and higher to pretty high loop order, if not forever.
Okay.
So, yeah. Sorry, going back to Song's previous question, there is an easy answer, which is you draw the cuts, the Feynman diagram that has the K3 surface in it. In this case, it's a 2-2-2 graph. And if you took that maximal cut, there's no way to assign it MHV helicity coloring. So you know that that cut has to vanish for MHV amplitudes just because there's no helicity.
Yeah, okay. Any more questions? All right, if not, let's thank Jake for this wonderful talk. Yeah, thank you.